All right, so yesterday we learned to do higher derivatives, and today we want to focus on what the meaning of the second derivative is, because it's very important to us. So let's read through. We've got a whole bunch of theory here. The second derivative gives us extra information about the curve that helps us to find its shape. We know that the second derivative is the derivative of the first derivative. We also know that the f dash x is the derivative of f of x. Thus, the second derivative and the first derivative have a similar relationship to the derivative and the original function. That is, they're both finding rates of things. So, we learnt in exercise 4a that if we find the first derivative and make it greater than 0, then we're finding the spots where the curve is increasing. If the gradient is less than 0, it means that it is decreasing. If the gradient is equal to 0, that means that we've found ourselves a stationary point. Here's the new part. The second derivative, I've got to just change these symbols quickly. There should be derivatives in there. The second derivative, when that is greater than 0, it means that my gradient is increasing. If the second derivative is less than 0, it means that my gradient is decreasing. And if my second derivative is equal to 0, it means that my gradient is stationary or flat. So this gives us a few things. Thus, it says, if my second derivative is greater than 0, then my gradient is increasing. This means that the gradient of the tangent is increasing as we move from left to right, because that's how we look at these, as we're moving left to right on our graph. And we say that the curve is concave up. That is in capital letters, because that is really the key idea here. If the second derivative is greater than 0, the curve is concave up. However, the f dash x part can be a little bit confusing, and here's why. If I look at this first curve, it makes sense. My curve is concave up, it's going upwards, and my gradient is positive and increasing, correct? This one, though, maybe doesn't come quite so naturally. Yes, it is concave up. The gradients individually, if I look at them there, they are actually negative gradients. But as I am moving from left to right, looking at those gradients, I'm going from -6 to -2 to -0.5. They're actually getting bigger. The gradients are getting bigger because they're going from big negative numbers to much smaller negative numbers, which means that my derivative is increasing, which is what it says there. Okay, so be careful with that because it's different to how we think about it. If we're looking at the gradients individually, yes, the gradients are negative, but as we're moving along the curve, they're actually getting bigger for the concave up. All right, the second type. If my second derivative is less than 0, and then my gradient is decreasing, this means that the gradient of the tangent is decreasing as we move from left to right. The curve is becoming less steep, and we say that the curve is concave down. So you can see for both of those sections there, they're both pointing down, concave down graphs. And here we have a positive gradient. Okay, so positive gradient this time, we think, oh, it's positive, but it's actually getting smaller and smaller positive. It is decreasing as I go across from left to right. Whereas this time the negative one makes more sense because, yes, they are negative slopes the whole way around and they're getting more negative as we go around. Okay? All right, that's... Oh. Keep recording. Okay, on the next page, if the second derivative is equal to 0 and the first derivative is also going to be equal to 0, means stationary, this means the gradient of the tangent is 0 as we move from left to right on the graph. The curve is neither increasing nor decreasing because it's going to be a point, and we say that the curve is changing concavity. It is where it is changing from a concave up part of the curve to a concave down, or a concave down to a concave up. It's this point in between that we're finding where the second derivative is equal to 0. There's a summary down below. Let's look at the summary down below. It's easier. So remember, if the second derivative is greater than 0, our curve is concave up, and for a point, it will mean that it's a minimum turning point if we've found a point there. If the second derivative is less than 0, our curve is concave down, and if we find the stationary point there, it will be a maximum. If the second derivative is equal to 0, and please note this part, it says, and the concavity changes. That's something that we have to check for, because not every time that the second derivative is equal is a point of inflection. We have to actually check that the concavity changes, always, always, and the question won't necessarily remind you to do that. Then it will be a point of inflection. There is a summary of all of that in a diagram form here. So here is our second derivative that we've just been learning about. If the second derivative is greater than 0, that means concave up. And you can see each part of these curves are all concave up. If my derivative is greater than 0 for each individual point, that means that we've got positive gradients coming up here. If my first derivative is less than 0, I'm going to have negative gradients for individual points. If it's equal to 0, I'm going to have my minimum turning point, but for the rest of my concave up curve around it. Yeah? And keeping going for this one, if it's less than 0, we have all the concave down versions, positive gradient, negative gradient. If it's equal to 0, it means it's a maximum turning point. And if my second derivative is equal to 0, then I'm going to be finding points of inflection. So if it's greater than 0 on both sides, that's just that kind of curve there where the gradients are positive on both sides. If the gradients are negative on both sides, then I'm going to have that. If I get the first derivative is equal as well as the second, so first and second derivative are both equal to 0, then it will be a special type of point of inflection which we call a horizontal point of inflection, where it comes all the way down to 0. Okay, question time. Number 1, does the curve y equals 2x to the power of 6 have a point of inflection? If I'm going hunting for a point of inflection, I need to find the second derivative. So first derivative will be, bring the 6 down, it will be 12x to the power of 5. Straight to the second derivative, y double dash equals 5 times 12 makes 60x to the power of 4. If I'm hunting for a point of inflection, I'm going to make that second derivative equal to 0 and see if I can find a point. So that will be 60x to the power of 4 is equal to 0. The 60 could divide away. The fourth root of 0 is still going to be 0. And because it's a point that I'm after, I would like to know the y value. So I would sub the x equals 0 back into the original equation, which would also give me 0. So we have what is called a possible point of inflection at 0, 0. It is not confirmed to be a point of inflection until I test whether the concavity changes. That was that part in that table I was trying to emphasize. To test that, we need to draw yet another type of table. It's going to be a concavity table. It's going to have our x values at the top. We're testing the concavity, so I want the second derivative for my second row. And the last one we're going to label concavity. So the x value, I've only got one point here, which was at x equals 0. Put it in the center, and I'm testing either side of that point. So obvious choices, as always, -1 and 1. If you sub -1 into the second derivative, okay, second derivative, concavity, it's going to be -1 to the power of 4, which is 1, times 60 is 60. The 0, if you sub 0 into there, it should be 0 because that's what we found. And if I sub positive 1 into here, I'm going to get 60 again. So what that means for my third row, if for the 0, that tells me that we have a point that is a point on that curve, and I want to test the concavity on either side of it. On the left, I have a positive 60, which means positive numbers mean concave up. So I'm drawing a concave up kind of curve there. The positive 60 on the other side also means concave up. So the concavity has not changed. I need one of them to be concave up and one of them to be concave down for this to be a point of inflection, and it's not. Okay, so unfortunately we have to say here, therefore, the concavity does not change, therefore no point of inflection. Now, if you think about it, you may be able to realize why that has happened. Remember drawing things like y is equal to x squared, there's our parabola. If I do y is equal to x to the power of 4, what does that do? It's just a parabola that's a little bit square at the bottom and gets steeper really fast. So x to the power of 6, it's going to be doing the same thing. It is the basic parabola shape, which means that point that I'm finding, algebraically I'm able to find a second derivative, I'm able to find an x value, but I'm just finding the turning point. It's not a point of inflection. Okay, so that's why we have to test the concavity to make sure that we've found a point of inflection. Okay, question 2. Find all the values of x for where the curve is concave up. As soon as we're talking about concavity, we're talking about the second derivative. So let's find it. Y dash equals 3 times 3 makes 9, x subtract 1 from the power is 2. Then second term, 2 times negative 5 is negative 10, x to the power of 1 plus just the 2. Second derivative, y double dash. 2 times 9 is 18x minus 10. For something to be concave up, do you remember the definition?
That's when it equals 0.
Yes, so we're going to say when y double dash is greater than 0. The second derivative was 18x minus 10, and that needs to be greater than 0, and I can now solve that inequality to find my x values. So move the 10 across and divide by 18 would be 10 over 18 or 5 over 9. So any value of x greater than 5 over 9 for that curve will be concave up. That's it. All that space that we had there. Let's have that one. Question 3. Find the point of inflection. Okay, so here's another one. Find a point of inflection very similar to question 1. So the same process. Find the first derivative. This time I need to call it f dash x though, because we're using function notation. So bring the power of 3 down, subtract 1 from the power. Bring the 2 down, multiply with the 5, makes 10x, and the minus 2 disappears. Second derivative, 3 times the 2 will make 6x plus 10. If I'm after a point of inflection, I'm now going to say that my second derivative must be equal to 0. My second derivative was 6x plus 10. Make it equal to 0, and we can solve for x. Am I going too fast? I am trying to make sure I get through it by the end because we've got a few questions here to do today. All right, move the 10 across and divide by 6. Yeah, so minus 5 over 3, or I don't mind if you go to a mixed numeral, which is minus 1 2/3. As soon as you find an x value of a point, we always want to find the y value. So y equals, and you'd get your calculator out, and you're going to sub that back into the original equation. I'm not going to tell you. I'll tell you what it is. What did I get? There it is. I got 196 over 27. So I have a possible point of inflection. At minus 5/3, 196/27. But I have to confirm it with my concavity table. So let's draw that over here on the side. The concavity table has the x values, the second derivative, and then finally concavity. My x point that I have found is the one that needs to go into the middle. So minus 5/3, which is minus 1 2/3. So something smaller than that would be negative, you want to go -5, did you say? You could. -2 is where I went. Something bigger, I went with the easy option. I went with 0, good, easy to substitute in. If you sub -2 into the second derivative, it's right here. So it's minus 12 plus 10, so it's -2. If you sub -5/3 in, you should hopefully get 0, because that's why we did that one. And if you sub 0 into here, 6 times 0 is 0, plus 10 is 10. So we've gone from a negative concavity, negative meaning concave down, to a point, and then from that point we're then concave up. So the concavity has changed, which means this one is a point of inflection. So the concavity changes. So therefore, a point of inflection at minus 5/3, 196/27. Okay. Then we get the questions that have it all together. Question 4. Question 4 says, use the second derivative, if possible, to determine the nature of the stationary points of the graph f of x equals x to the power of 4 minus 4x cubed. Also, find any points of inflection, examine the concavity over the whole domain, and sketch the curve. Just a few little things we want to do here. Okay, so to this point, we have used a table with our gradient to work out whether our stationary points are maximums or minimums, but now I'm going to show you that we can use the second derivative as a second option. Sometimes you may not want to use a second derivative. If you have an equation that is hard to differentiate once, you don't want to differentiate it twice, okay? And so you'd want to use the table method. Okay, but if something's easy to differentiate, this can be faster. Okay, so let's do this one. If I have my equation, f of x equals, there it is, I want to find my first derivative, f dash x equals 4x cubed minus 12x squared. Now, to find my stationary points, I will make my first derivative equal to 0 and solve for x. So first derivative equals 0 equals, now if I'm solving this, I'm going to want to factorize it. So I'm going to factorize a 4x squared out, and that will give me x minus 3. Solving that equation from there, either the 4x squared is 0, which means that I have zeros at x equals 0. Liam, you all right? From here. The other 0 is 3. So x equals 0 and x equals 3. Straight away, find the y values of those points. Y equals, sub back into the original equation. Putting 0 in here, we get 0. Putting 3 into there. 3 to the power of 4 minus 4 times 3 to the power of 3 is minus 27. Okay, so there's 2 stationary points, but I want to know whether they're maximums or minimums. So this time, for something new, we're going to use our second derivative, f double dash of x. So looking from here, differentiating this again, bring the 3 down the front, will bring 12x squared minus 2 times 12 is 24x. Now, to test here, what I'm going to do is test each of those x values by subbing them into that second derivative. So I'm going to use the when x equals 0, and then I'm also going to do the when x equals 3, the two x values that I had for my stationary points. Sub them into this second derivative. So f double dash of 0, because I'm subbing in x as 0, 0 into here would be 0 and 0. Oh, it's 0. What does that tell me? First derivative was 0. Second derivative was 0. It's a possible horizontal point of inflection. I still have to say possible until I test the concavity. Okay? But it's not a stationary point we've just discovered. It's going to be some kind of point of inflection probably in there. Okay? Let's try the other one. Actually, I better write that down there first. So let's write possible point of inflection. We'll come back to that one when we do our points of inflection. For the other one, f double dash of 3. Subbing 3 into here, 12 times 3 squared minus 24 times 3 gives, anyone done it? 36, good job. Because that is a positive number, meaning greater than 0, that is where the curve is concave up, meaning that point is down the bottom being a minimum. So that means it's a minimum point at x equals 3, y equals that one, minus 27. The y value that we found earlier, not the value of the second derivative. Okay, so there's our stationary points done with our new method of the second derivative, but we have to do more than that. We are also asked to find points of inflection and look at the concavity part of this as well. So moving on. The second derivative, we've already found it, but if I'm looking for points of inflection now, what do I have to do? Make the second derivative equal to 0. Okay, so let's do f double dash of x is going to be equal to 0. So my second derivative was up here. That means 12x squared minus 24x is equal to 0, and I want to solve that to find x. Factorize it. I can bring a 12 out and an x out, which will give me x minus 2 inside. The solutions to that are going to be x equals 0, no surprise there, because it's this one coming out again. And the second one is x equals 2. So there's actually 2 points of inflection in here. We had one of them come out earlier as a horizontal point, possibly, and we found another one that would just be a normal point of inflection, not horizontal. Okay? So, but to make sure, you can't ever just find the x values, you find the y values as well, but you have to test them in your concavity table. The y values though, before I move on, find the y values of those points. We already know that that one's 0 and the other one's minus 16, thank you. Concavity table. We need a few points on the x here because we've got 2 of them. Second derivative. Oh, that was interesting. Let's try that again. So it's f double dash of x. Oh, it's changing into a box on me. That's weird. Undo. Can I undo that? It's an automatically upgraded, and then just delete it again. Okay, so we've got 2 points, 0 and 2. So I need space, 0, space, 2, another space. Yep, so minus 1 for lower, in between would be 1, and 3 would be above. It spaces it beautifully. So for 0 and 2, they're our horizontal points of inflection. Or not both horizontal, points of inflection. So they will both be zeros and they will both be points. When we sub in -1 into the second derivative, so into here, or the one further up if you want it in f double dash of x equals, -1 would be, do you want me to tell you the answers? 36 for that one, -12 for that one, and 36 for that one. Okay, please check them sometime when you have some time to make sure that you're subbing into the correct things. Positive 36 means concave up, -12 means concave down, 36 again means concave up. So on each side of those points, the concavity is changing each time. So they are both points of inflection. So I'm going to say, therefore, 0, 0 is a horizontal point of inflection because its first and second derivative was equal to 0. The point 2, -16 is just a non-stationary point of inflection. So I'm just going to say is a point of inflection, just an ordinary one, not stationary. I still have to draw it. We still have to try and draw it in there. I hope you'll have some space to the right. To draw all of that information, let's draw a graph. Most of it's happening on the right-hand side of the y-axis. Okay. So first of all, we found that we had 2 points that had 0 gradients, which we thought, well, this first one, 0, 0, turned out to be a point of inflection, a horizontal point of inflection. But we found a stationary point, which was a minimum, at 3, -27. So that's going to be 3, -27 down there. We also found that we had another point of inflection at 2, -16. So that can be about there. So the minimum can help to draw that little curve on there. It's going to come up through that point of inflection. Now this, when it goes through the origin, it has to have another point of inflection there, and you need to try and make it look like it's going horizontal. So it's a bit like a cubic bend. So come up, kind of flatten off, and up like that. And you can extend that a little bit further that way if you'd like. Okay, so approximately what my curve looks like. Very much not to scale, but there you go. So that question has a lot in it because you're doing everything. You're finding stationary points. You've got to find out what type of stationary points they are. You have to find points of inflection and sketch it. Tom?
Well, how did we try and find the first derivative? Why did we find the first derivative at the start?
Because in the question, it asked me to find the stationary points and determine their nature.
Okay, and
so, yeah.
Does the first one determine if it's vertical or horizontal?
The first derivative.
Yeah.
The first derivative works out when the gradient is 0. So it finds the stationary points, but it will also find a horizontal point of inflection, which is what happened there.
And how do you find the differences other than the second one?
The second one tells us where it's concave up and concave down. So it found, so here where it changes, this is concave up here, and then it'll be concave down that way. So there's a point of inflection here.
Yeah.
And then this one was my horizontal, so it's concave down to concave up. So it finds those 2 points of inflection. Okay? But you always have to test points of inflection with your table. Okay guys, let's keep going. We've still got a couple to do. Question 5. For what values of b is that lovely equation there, concave down when x equals 2? Concave down, second derivative. So differentiate, y dash equals 4x to the power of 3. Now the b is just a number. Bring the 3 down and it will be -3b x squared to differentiate that second term. 2 times 5 is 10x and plus 6. Second derivative, let's do it again. 3 times 4 is 12, x squared. 3 times 2 will be minus 6bx. and plus 10. Now it's telling me that I want the curve to be concave down. Concave down means what for the second derivative?
Has to be lower.
Less than 0. And it's going to be less than 0, it says, when x equals 2. So there's some information for me to put into my equation. So the 12x squared, that part there, I'm going to sub the 2 in. 12 times 2 squared minus 6b times a 2 plus 10, that's my second derivative, and it has to be less than 0. All that's in there is the b and some numbers, so I want to get that b by itself. So that's 4 times 12, so that's 48. In the second term, minus 6 times 2 is minus 12b, plus 10 is less than 0. So minus 12b, 48 plus 10 is 58. So let's move it to the other side to be a negative 58. And then if I divide by negative 12, it's an inequality, turn the sign around, and it will be 58 over 12, or 4 and 5, 6. You can simplify the 58 over 12, but I went to a mixed numeral. Okay, question 6. These last ones shouldn't take much time, but we do need to try and get through them. Question 6 wants me to, for a particular curve, I know that f of 3 equals minus 4. That is talking about a point on the curve. Then it tells me the gradient at 3 is negative, and the second derivative at 3, which would be the concavity, is positive. Can I draw a curve at this point, just at that particular point, to show the shape of what is happening there? So very briefly, I can't do much. I don't know all the rest of the graph. All we know, actually, sorry, draw that higher because it's at negative 4. This first bit, 3, negative 4, that's the point on the curve. X is 3, 1, 2, 3, and Y is negative 4, 1, 2, 3, 4. So there is the point. That's the first part of the information. This one, gradient at 3, so that's talking about the gradient at that point, is negative, which means it's got to be sloping in the negative direction. Also, if the second derivative is positive, it has to be negative but concave up, because positive second derivative is concave up. So that would mean something like this. Negative slope, but curving in the concave up direction. As I said, I don't know what's happening anywhere else on that curve. I haven't been given enough information to go any further than that, but we're just looking around that point. Last one. Question 7. The curve below, and this question is a little bit of a test your understanding on what all these different things mean. You're not drawing anything, you're not going to be differentiating anything, but can you interpret stuff from the graph that you've been given? So it says from the curve below, it shows the number of unemployed people, P, over time T months. Describe the sign of the first derivative, because dp over dt is first derivative, and d squared p over dt squared is second derivative. So first derivative is the gradient. What is happening with the gradient of that curve? All of it. Everywhere along that curve, it is always negative. So it is less than 0. What about the second derivative, which talks about the concavity? Yes, that curve is always concave up, so the second derivative will always be greater than 0. Now for the wordy parts, Tom.
Why is it always concave up?
Just for that part that's drawn there, that part is always, it's going up, it's concave up direction.
Oh.
Okay. Part B. How is the number of unemployed people changing over time? So as yes or decreasing. So if we're talking as we're going from left to right across here, we're starting with quite a high number of unemployed people, and we're getting less and less, as time passes, there is less and less unemployed people, right? So the number of unemployed people is decreasing over time. Okay, C. Is the unemployment rate increasing or decreasing as we're going across in time?
Sort of decreasing until it kind of levels out.
You got to be careful.
It's a lot, and then smaller. And
Correct. Okay, so yes, let me see the graph here again. As we're looking at the gradients of that curve there, they are negative gradients. So the temptation is to write down that they're decreasing. But these are very steep gradients. So you could say this is like -5 up here. But as I come down, it's getting shallower and shallower. So it might be -1 about here and getting very close to 0 as I get towards the bottom. So the rate that it is changing is actually increasing. Okay? So I'm going to...
Is it a decreasing slope?
So this is how I'm going to word it. I'm going to say the number of unemployed people is decreasing, but at an increasing rate.
So there are less unemployed people.
Yes.
Which means there's more unemployed people.
Yes.
The
rate is going back up.
The rate is going back up.
Yes.
We can't say that.
No, it's because they are decreasing. What?
If that trend was to continue, we'd soon be back to having the same number of unemployed people because that's actually increasing.
Yeah.
We don't actually have the equation of it, so we can't make